We're now going to look at a second inference problem. The first inference problem focused mainly on inferring the parameter. The goal of this second inference problem is to talk a little bit about what we want to do with those parameter estimates, because these parameter estimates are not often used in isolation. If you're deploying a self-driving car that needs to take actions based on what it thinks the driver has said, for instance, or what it thinks its vision system has interpreted from the environment, we're going to need to translate these estimates of what's going on in the world into actual real-world decisions. And we're going to need a little bit more theory in order to carry that out in some optimal way. And that theory will be called Bayesian decision theory. It connects to ideas like reinforcement learning as well. And so this problem we're going to look at is going to be a very simple a problem that's designed to sort of try and understand some of the principles behind that theory. Okay, so what is the inference problem? Well, it's going to involve Alice, and it's kind of topical because we could couch this in terms of COVID if we wanted to, which is that Alice is going to have a test for a disease. And we're going to introduce a bit of notation. So A indicates that Alice really does have the underlying disease. So it could be Alice is COVID positive, and A is equal to 0 indicates she's negative. She doesn't have the disease. And the test result we're going to indicate with B, it's going to be a binary test result. Either the test indicates that she has a positive test and she does have the disease, or B is 0, which indicates she tests negative. Okay, so far so good. This will look like a fairly familiar problem, at least to begin with. The test, and there's been a lot of discussion about this in the context of COVID, but this particular test is 95% reliable in the sense that in 95% of the cases, people who really have the disease, a positive test is returned. And in 95% of the cases of people who do not have the disease, a negative test is obtained. Okay, so it's 95% reliable in both of those senses. And we know, because of things like the ONS survey, that 5% of people with Alice's demographics, so her age, her background, etc., have the disease. So before we've taken the test, we would say, I think there's a 5% chance that she has the disease. And of course, the question here, which has dominated much of Twitter for COVID, is what happens if Alice takes a test and the result is positive? What is the probability that Alice really has the disease in this case? So what I would like you to do now, so this so far is not, I should say, about decision making. We're going to come on to the decision making in just a second. This is purely a question about inference at the minute. Let's take a couple of minutes to stop the video, if you would, and take a pen and paper out and try and compute this probability, the probability that she is positive given that the test result is positive, the probability that A is equal to 1 given B is equal to 1, if you want to couch it in our notation at the top here. Great, so hopefully you've taken some time to do that. Let's run through the way that I calculated this. We'll do it in excruciating detail just to make sure we haven't lost anyone. So remember, the first thing you do when you hit an inference problem, if you cast your mind back to the end of the radioactive decay example, is you write down the probability of everything. That was given to us in the question. And that probability of everything can be thought of as a little toy statistical model that has generated our data. So in this case, the statistical model comprises two variables. It comprises the variable A, which is whether she has the disease or not. And we know with probability 0.5, she does have the disease. That's this arm of the tree out here. And if she doesn't have the disease, A is equal to 0, and that will happen 95% of the time with 0.95 probability. Okay, so that's our prior on A, whether she has the disease or not. No data so far, so this is just our prior assumptions. Okay, great. And now we can write down all the arms corresponding to all the possible test results. So if she doesn't have the disease and she takes a test, there's a 95% chance that the test comes up negative and a 5% chance that it comes up positive. If she does have the disease, there's a 5% chance that it comes up negative and a 95% chance that it comes up positive. And this now is our full joint distribution over all of our variables A and B, and we could traverse down the tree in any way, any of the 4 ways we like, in order to work out, say, the probability that A is 0 and B is equal to 1. We would just take these probabilities and multiply them together in order to get that setting of the variables. And so I can summarize this tree with this table, which does exactly what I was saying there. It traverses, every possible route through the tree, each one of the 4 combinations, and just multiplies the probabilities out. This is the joint distribution over all of our variables enumerated together. Great, and notice, just as a side note, in order to go from here to here, I've essentially used the product rule of probability that P of A and B is equal to P of A times P of B given A. Okay, elementary application of the product rule when you've got binary variables. Great, okay, so armed with that, having made everything explicit, we're now going to be interested in what happens when B is equal to 1, i.e. the test has come up positive. And there are 2 arms of our tree when that happens, 2 leaves on our tree when that happens, and that corresponds to this row of the table. Okay, and I'm going to now use Bayes' rule to compute our posterior distribution over A, our unknown or latent variable, given our observed variable B, the test result. So in particular, I'm going to compute the probability that the test, that she has the disease, that A is equal to 1, given the test is equal to 1, that the test was positive. And we know that we can just apply Bayes' rule on this. And so the right-hand side is sort of computing Bayes' rule. And then we can go and plug in all of the values from Bayes' rule. So for instance, this one we already have, the probability that B is equal to 1, given A is equal to 1, this is equal to 0.95. It's sort of this probability here, right? The probability that A is equal to 1, well, we know that's this thing here, is 0.5. This one at the bottom is a bit more problematic. What's the probability that B is equal to 1? For that, we have to use the sum rule in order to calculate it. And you can view that as just summing over both of these elements in the joint distribution. We're marginalizing out A, or put another way, we could just plug in the product rule down here. This is, the sum rule down here. So this is the sum rule, and it's equivalent to just summing these 2 terms in the table together. Again, I'm going slowly here and trying to tie all these perspectives together in order to try and make everything completely explicit. So sum rule. Good. And now we're free to substitute in for all of these things. The values are in this table, so both of these things take the value of 0.95 times 0.5. This is 0.05. Be careful of my decimal places there. Times 0.95. So both of these terms are the same. And remember, this top term we said is 0.95 times 0.05. So once you substitute all of those values in, perhaps fairly obviously, because these 2 terms in the table were the same numerically, the probability that she had the disease given the test result is 1/2. And this is a famous fallacy, sort of trivial mathematically, but a famous fallacy that comes up because the layman on the street will often say, if the test is 95% reliable and you take a test and it comes out positive, oh, that means there's a 95% chance that I have COVID. When actually, because the prevalence is very low in the community, and so the a priori chance of you having it is relatively small, it's more likely, or just as likely in this case, that you don't have it, but there was a false positive on your test. And this sort of argument has, of course, exploded across Twitter until fairly recently, with the controversy about false positives from COVID tests driving the rates of high positive testing across the community. Of course, the fallacy in that argument as applied to COVID is that this 0.95, this 0.5 figure down here, that 5% of people's age and background have the disease. People have used the ONS statistics for this, which draws a random person from the population out who does indeed had, roughly 1 or 2% chance of having COVID at the moment. But of course, the people that are getting tested are not random draws from the population. Instead, they are people typically who have symptoms. So if Alice had a test because she had symptoms, that means that it's not 5% probability or 2% probability, say, that she had COVID. Rather, there's a much bigger chance that she had COVID because she's showing signs, and that changes the calculation quite dramatically. And I think it's fairly uncontroversial to say that the false positives are not driving the high test statistics, and it was kind of crazy to say so to begin with. Okay, so to recapitulate, what we have done is we've just solved an inference problem. We've seen some observed data, a test result, and we've used it to compute a distribution over an unobserved quantity, whether she has the disease or not. And there's a 50% chance she has it and a 50% chance she doesn't have it. And now we're going to get to the nub of the question that I really want to answer through this example. And that question is the following. Alice has the test and the result is positive. So this is just recapitulating the setup we had before. And now the question comes to about how we should treat her given this information. So we're going to introduce this new variable t, and that's to do with decision making. So t is equal to 1 indicates we are going to treat her. We're going to take dexamethasone or something, a steroid, an anti-inflammatory, and we're going to treat her with that. T is equal to 0 means we're just going to let things go for a bit, and we're not going to treat her. And based on some medical trials, we've got some measurements of people's quality of life when they undergo treatment, in the cases where they have the disease and in the cases where they have not, i.e. the control arm of the trial. So here are some quality of life figures that have come out of that trial, and they're sort of displayed in this little matrix. Let me talk through the elements of this matrix, but I think it's fairly intuitive. So here, R is going to be the quality of life. R is going to stand as a proxy for reward. And if you don't have the disease and you have no treatment, you're going to be at your maximum 10 quality of life units. You're going to dawdle along just like normal, with no change. If you don't have the disease and you have some treatment, the treatment does have some side effects. So steroids have some side effects, and they impact on your quality of life. And this study has said that it reduces your quality of life by 30%. You only have 7 quality of life points now rather than 10. If you have the disease and you don't have the treatment, it's really quite bad and unpleasant. And you have 3 quality of life points for the duration that you're infected, say, which is a substantial reduction on your 10 that you'd normally get. And if you have the disease and you have the treatment, it's not perfect, but it does improve things. Okay, so you have 5 quality of life points in those cases. So it's roughly half the quality of life you would have had if you didn't take the steroid and you didn't have the disease in the first place. Okay, so these are the various different possible outcomes and given potential underlying states of the world. And the question is, given our knowledge about Alice, should she be treated or not? We know there's only a 50% chance that she's got the disease. So given this set of possible quality of life scores, which one should we take? And so what I want you to do now is to pause the video again and just spend a couple of minutes trying to figure out what you think the right answer is. Even if you don't get to the right answer, just figuring out roughly how would you go about answering this problem in the first place. What would be the principles that you would use in order to solve it? Great. And when you've done that, we'll go on and run through something which is very fancily called Bayesian decision theory, which is the way of computing the answer. And essentially, it is just about computing average rewards or average quality of life scores given possible underlying states of the world. So you're averaging out, I should say, the underlying state of the world, which is unknown, and computing the average rewards given treating or not treating, and comparing the two and figuring out which one gives you a better average expected quality of life. Okay, so at the top here, I've just recapitulated what we know already. We've already computed the posterior. That was the first part of the question when we said there was a 50% chance that she has the disease given that the positive test has been returned. And this was just recapitulating all the different quality of life scores, aka the rewards under the different settings of the true underlying latent variable A and the treatment that we're going to apply or not. Great, so this very fancy term Bayesian decision theory just says what you do in order to figure out your action is you compute what's called the conditional reward. And the conditional reward is the expected reward under giving the treatment and the expected reward under not giving the treatment. So that's the setting that t is equal to 1 and t is equal to 0. You compute them in both cases, and then you pick the action which gives you the largest conditional reward. And the way that the conditional reward is computed is you take your posterior distribution, which captures your uncertainty in the state of the world, in this case, whether she has the disease or not, and you sum over all possible states of the world. You compute the reward for that state of the world given that action you're taking. So this might be she has the disease and you've treated, and you weight it by how plausible you think that world is. So what's the probability that she actually has the disease given the test result came back positive? So it's just weighted averages, essentially. No, nothing special. One really nice thing, and this I should say is sort of the right way, the optimal way to do it under the probabilistic approach that we're taking. The nice thing about this result is that we can separate inference and decision making. So when we talked about the radioactive decay example, we just talked about inference and we didn't talk about what the downstream task that Lander was going to be used for, other potential physics experiments, for instance, or ways of designing safety equipment or things like that. We didn't need to talk about that because it turns out the optimal thing to do is compute the posterior distribution regardless of what decision problem you're going to go and solve, and then for that particular decision problem that you're going to solve, compute R of so the reward function, which depends on the action and the underlying state of the world, and then compute averages over the posterior distribution. And so different decision problems will have different reward matrices, but you will always be using the same posterior if you've got the same information that you're trying to attack that problem with. So you can separate inference and decision making, which is a nice property. Okay, so let's run that through for our particular example. So let's take the expected reward, the conditional reward for no intervention, so no treatment. So we go and plug in this in here, and we sum over the two states of the world. So the R is equal, A is equal to 0 to start with. So we get this term. This term in our matrix, of course, is this thing up here, which is this one. So this thing is 10. And we weight it by the posterior. The posterior, of course, is a half. It's a half for all these examples. And then we have the other possible state of the underlying variable, which is that she does have the disease. So this is what reward we have, what's her quality of life if she has the disease and she does not undergo treatment. So that's this one here, obviously, which corresponds to 3. And again, we weight that by the probability of that outcome, which is again a half. And then we add 10 times a half to 3 times a half, sorry, and that gives us 6.5 points, 6.5 quality of life points if we don't treat. And then we do exactly the same thing for the treatment, and that corresponds sort of the other column of the reward matrix at the top, and gives us this sum. So it's 7 and this is 5 times a half. And if you work that through, you get 3.5 plus 2.5, which is just 6 average reward points. So in this case, we wouldn't prescribe dexamethasone. We'd say we're not certain enough that you've got the disease, and there's more of a downside from taking the dexamethasone, the treatment, than there is from actually you know, the upside if you had the disease and it would sort of make things a bit better. No, it's better that we leave things as they are for the minute. Great, and you can sort of see that from the payoff matrix that if she doesn't have the disease and you treat, you lose 3 quality of life points, and if she does have the disease and you treat, you only gain 2. So given it's a 50-50 chance, we would probably have expected that we shouldn't treat because of this asymmetry in the reward.